Okay, so dear audience, I'm very happy to share some data and my thoughts with you today. Many thanks for inviting me. So my work is dedicated to the investigation of event prediction, including both simple and more complex events, such as actions, which I'm focusing on today. So, well, event prediction is omnipresent in everyday life. So some kinds of prediction just happen to us. For instance, if you listen to familiar music, sometimes we need it when we engage, for instance, in a conversation. And other types of prediction are really essential. So, for instance, if we want to avoid or induce collision. So I think all these types of events are out there, and we have to cope with them, and they also mix up in a certain way. So, and against this backdrop, it's not too surprising that experimentally we can have a multitude of predictive phenomena that we can investigate in the lab. So, for instance, you see that reaction times are dropping if you prepare to certain stimuli, or also motorically. Or, for instance, we get large negative going variations or ERP components if we are preparing for a certain event, or shorter deflections if our semantic expectation is violated, for instance, here in language. Or we get a reduction or attenuation of a signal in the brain in the bold response if we are, see a certain stimulus over and over again, for instance, here in fusiform gyrus. So, so there's a broad variety of different phenomena, but they all, in a way, converge to main effect classes, if you wish. The first is that there's a kind of pre-activation if we are successfully predicting events. So there's a kind of faster processing, a faster search, faster selection, and what we might call, on the other hand, a better focus, so reduced costs for processing what is now when we are prepared for it. So, and well, in a way to classify predictions it's a pretty simple approach, is to look at the memories that our predictions are exploiting. So when we have a stimulus, we have a sensation. The sensation enters sometimes or often our working memory. And based on this working memory, we are able to engage in expectations. So, for instance, here, I think this type of, working memory from recent sensation helps us to estimate state change, so dynamic forward kinds of predictions, for instance, so what I call transformation. But many everyday events require, let's say, our long-term memory, so they are more complex. These are, for instance, predictions that exploit semantic information, episodic knowledge, and frequencies, also statistical information. So this is what I call the prediction of transition, not transformation. Okay, and so I think both types of prediction are essential in everyday life, and I also think that they partly engage different brain networks. And on the one hand, state change or forward prediction, I've investigated a pretty long time using a serial prediction task. So this draws on some premotor parietal areas I very shortly refer to today. But on the other hand, if you go for these more complex predictions in everyday life, for instance, using action observation as a paradigm, we have additional areas that feed this prediction and restrict this prediction based on long-term memories. And just to mention very quickly this network, it's the only slide about it in this talk. This forward state change or prediction, this simple prediction, if you wish, based on quite a number of studies, I suggest that the premotor cortex and, of course, also associated parietal sides is the area or is the network that is most engaged in this forward state change predictions, no matter whether these are rhythmic predictions, object-based predictions, or spatial predictions. And we know that this cortex is also relevant for preparing and planning actions of different effectors, and that is an interesting correspondence in my view. So we needed to, just to mention, it's not only that you get this cortex being engaged if you monitor kind of abstract sequences for these structures to engage in, but it's really important that you try to come up with a certain expectation of upcoming stimuli. It's not just monitoring, it's really prediction. And the correspondence I was talking about is that between these different types of perceptual predictions and the motive factors that are also driven by or controlled by these areas. And this is for the rhythmic predictions, an area which is important for vocalization, articulation. The object-based predictions draws on the areas for manipulation, object interaction with the hand, and the space-based prediction are mostly engaging the dorsal premotor, which is important for reaching and pointing. So, and based on this correspondence, which I just mentioned here and not really go into further details, led me to suggest that the motor system serves the prediction of change at the senses, no matter whether they are self-induced or externally induced. Of course, there are areas which distinguish between it, but I don't think that premotor cortex does so much. But skipping further details and going more for these real events in life, I was addressing now for several years. I'm interested in action observation, and what I mean with real events, they are essentially spontaneous because you never know what kind of change in the environment becomes important for you. So you have to prepare or react spontaneously to all this kind of change. They are multidimensionally, of course, and also probabilistic. So real events of this kind constitute, let's say, language or music and action, and it's action I'm focused on. Okay, so so I have two major interests in action, and the first is I want to find out what kind of information is exploited to understand what manipulation we see. So typically in a, let's say, a 2-second window on an action, we have this manipulation, of course, but we immediately also have access to actor information, room information, and of course the objects that are involved. Okay, so that's one interest. And the other is, so the history of this action with regard to other objects and manipulations, actors and rooms. Okay, so all of these different types of information that precede the action also, of course, change what we expect in this very action to happen. Okay. And well, what is important, as I'm interested in a spontaneous exploitation, I investigate this on an implicit level. That is, we never instruct subjects to focus on actors or rooms or objects. They are just asked to report sporadically what manipulation they saw on the previous trial. Okay? So that's for all studies I show now. It's just implicit. All the effects are just happen in the brain. And subjects mostly don't know if you ask them, okay? So, regarding, so what I will do now is I start with some studies, pretty recent studies, so I'm not quite sure about all details of the effects we found, but in this context, I try to make some sense of it. So, some studies on the probabilistic structure of action. So that's on the history side, if you wish. And later on, turn to some studies where it's more about the information exploitation in a little scene, like objects and rooms and so on. But starting with the probabilistic structure, well, you can think of actions made of sequences of stages or nodes that are connected to each other, so action steps. And these action steps can be defined as the most invariant stage in an action that have to occur in every effective action sequence. Okay, so this is dovetails in a way with an old definition provided by Byrne and Ruston, who observed in great apes certain behaviors that are highly variable, but they all show the same basic action step pattern across and within individuals. And this is just to show it in individuals that are shoelacing. And you see you can derive more than 70 versions only from these 9 subjects to lace shoe, but all somehow converge to a certain sequence of 3 action steps. Otherwise, you don't lace a shoe successfully. Okay, and these action nodes, something very special is happening in my eyes. So if you compare or let subjects segment actions, like this example above, and let's just ask them, press the button whenever you feel that a certain action step or a certain meaningful structure has emerged, and you ask them to do it in a Tai Chi control condition, you find at the points where they press the button, an increase in area MT, which is sensitive to motion. So I think for both conditions, it's true that change in certain dynamics of the body, for instance, slowing down or increasing of tempo, might be relevant for both to trigger this very moment. But what is important in an interaction between both conditions, it's only in actions that we find a frontoparietal network that is transiently increased at this point, at these nodes. And if you look at the areas themselves, so I just go through this very quickly, but we think it seems as if at this point you have a recall from long-term memory that helps you to feed the expectations on the next action steps, so and to reorient also your attention in the scene. Okay. So the title of this paper is, therefore, the fraction of an action is more than a movement. Okay, so there is something in these action steps, of course, so there's a kind of fluctuation between informed and less informed prediction. And this is what we also investigated in this study here. So what we might refer to objective uncertainty of prediction increases when approaching nodes, because nodes connect two actions, right? So where you know what object is grasped, your certainty is pretty high, and then you are uncertain about what the next object will be. And here we manipulated this objective uncertainty with using a first-level statistical structure in a simple Markov matrix. And what we did here is to dissociate two different aspects of this prediction uncertainty. And there says, on the one hand, the predictedness of a certain action step. So predictedness means just that the probability of this object at this point in time is higher or lower. And on the other hand, the predictability or entropy of the stimulus, that is, two stimuli I compare that are equally surprising in a way, but there are more or less alternative actions at that point, and that renders the predictability higher or lower. And what we find is that you can, or what you see is that there are different areas going with these two types of, predictive uncertainties. And this is on the one hand, if you look for this predictedness or surprisal of an action step, you get a transient increase in the intraparietal cortex in both sides. And on the other hand, predictability or entropy goes more to prefrontal sides, including BA10 and orbitofrontal cortex, but also BA8 mesial. And it reminds me a little bit on the first talk we had today on this confidence. So in a way, it's about the volatility of the environment at this point, and you can quantify it, okay, and show that the bold response in these areas co-vary with a quantifiable amount of predictability. Okay, and but in everyday life, of course, we don't have just two action steps in an action. We have much more. And so the general idea is that, for instance, if you see somebody while you grasping a water boiler, you expect him to make tea, but this prediction is even more secure or stronger if you saw him before, let's say, preparing teacups or so. And this prediction changes if you see him handling with a decalcifying or so decalcifier, then your expectation would be that the water is put away, right? So what we here did in another pretty recent experiment is to add just a second level statistical structure that is independent of the first, and this is very important, otherwise we couldn't model those independently with regard to the Bold effect. And so what you see here is just, on the one hand, the quantification of information provided by the last action, and that provided by the second last. But we look at the beginning of the present action called action N at this point. So it's just always the same moment in time, but you just look for the information provided by the last and the second last action. And in a nutshell, what we find is that the last action saves costs in preparing for the present action. We have a decrease in lateral premotor sites that are interested in object grasping, so that's the ventral one, and also occipital and temporal areas. And but interestingly, reactivating the second last action costs. It comes with costs, and the more it modifies the last action, okay? So just the occurrence of the second last action modifies the informational impact of the last action, okay? And this is, the brain invests, obviously, in using the second last action to improve prediction, although, to repeat that, subjects didn't have to, right? In this paradigm, it's totally unimportant to be prepared for anything because you are just sporadically asked what you saw before, right? And what is now most important for us, and perhaps here most interesting, is there's an interaction between these levels, showing the less information can be derived from the last action, the more the brain invests in the second last. So we have an interaction effect that if you, in a way, it's a kind of conditioned exploitation of the second last action based on your last informational status, okay? And what we are now pretty interested in is this BA8 activity. Again, it shows that perhaps there's some reference to this first talk today, so that if you're not very confident in your own informational situation because the last action didn't help you to increase your predictive power, you go back to the second last, the more, right, and get more information from there. And this very same area also figures in a different experiment where we were looking for an emerging bias for one action over the other. Again, in an action observation paradigm. Again, it's task irrelevant. So it's just that we let subjects implicitly learn certain episodes that later on in fMRI diverge at a certain point in time. So I show you again, I hope. Oh, sorry. So they start the same. So this is pre-fMRI, this is post-fMRI. You see that the beginning is the same, and but then it diverges. It's a slightly different course of the action. And what we see here is now that what we did is that we presented one version 3, 6, or 9 times before fMRI and 3, 6, or 9 times in fMRI. So we have a situation where you get more or less a balance between both expectations, the one version or the other, or a bias. Okay, so you're biased towards the previously learned or the presently experienced version. And when we look at the point of divergence, so where then episodes split, we find an increase in anterior cingulate cortex, which we think might show that there's a bias or conflict signal delivered by ACC to adjacent, let's say, frontal polar cortex, but also orbitofrontal cortex, which might then be more engaged in the weighting and evaluation of competing options. Okay? Again, that's not a decision situation for the subjects. It's just a decision that the brain is making. Okay. So these studies so far, I've reported so far, show that the brain spontaneously exploits statistically structure and observed action, that is frequency-based structure. And there's a quantifiable amount of predictive power or impact at action nodes that is used and that can be shown by bold response. And turning now to the second issue, that is more related to what kind of information is used or, well, read out from a given action, from the now action. I will confine myself very much to the frontal-lateral cortex, also based on my own studies before. And the first point is that we expected that manipulation and object exploitation draws on the ventral premotor cortex as an area that is interested in object state change, that is manipulation. Okay? And on the other hand, we expected that adjacent ventral prefrontal area, including more, well, 44 perhaps, but 45, especially in 47, which might be more important for restricting expectation by exploiting semantic and episodic associations. So the room, the actors, but also episodes, and so on, scripts. So one of the first studies here were to look at, or if you're interested in what brain areas are processing manipulation information, you have a problem because actions are naturally confounding object and manipulation information if you want to use a natural, ecologically valid action, right? So what we did was, since manipulation comes with objects, we introduced the switching paradigm and just look for the switching effects. Switching is not task switching here, but just perceptual switching from one video to the next. So what we did was we were switching either the object from one movie to the other, or the manipulation, like here, or both. And so we can contrast the impact of either object or manipulation novelty, if you wish, at this point. What we find is that if the brain notices switch of an object, we get fusiform gyrus activation, which is not too surprising, as this area is interested in objects, both visually and haptically. But for switch of manipulation, we get both the ventral premotor and adjacent ventral prefrontal cortex. And so coming back to what I, on the last slide, showed, we now had two ideas that are now more detailed in the next experiments I show. The first is that ventral premotor could be relevant for the selection of possible manipulations based on the object. That is state-state transformation, so an object being changed or combined. This is the next slide, next experiment. And ventral prefrontal cortex could be more important for the selection of possible goals. That is an association between changes or manipulation. Okay, so that's in a way the next level of complexity. And this I will address in experiment 7. So, well, one approach to ventral premotor role in manipulation is to start with the idea that objects imply manipulations. Okay, this is not affordance, but it's referring to the idea that if you see a certain, like a bottle or a glass or whatever, you're just trained to associate or used to associate this object with certain actions. And typically, these are 1, 2, or sometimes 3 actions, rarely 4, with the same object or object pair. And we assessed this parameter, we call now implied number of actions, from objects in a different sample. And now the hypothesis was that ventral premotor cortex should increase with the number of competing possible actions if it's important for the selection of the manipulation, right? It should correspond to this competition that is just provided by the mere exposure to an object, okay? So for instance, you have actions where you have only one, where objects just imply one single manipulation, like here, putting jam on a bread, or sometimes you have 2. So for instance, peeling an orange or cutting an orange, then you see the manipulation, see, okay, it's peeling an orange. And we also had sometimes this kind of stimulus. Did you saw that? Can you recognize what you see? It's a cracking an egg with an orange. So why do we use this? That's very, very important, because we want to disentangle the implication of the object itself and the manipulation. And that is, we would expect ventral premotor to co-vary positively with this implied number of actions, but only if the observed action is among the implied ones. Right? If it's a pantomime, you have an unrestricted research in memory, what this pantomime could mean, so what this manipulation is good for, or is meaning, right? So the object doesn't help you to restrict your expectations. So that's very important. So, and this is what we find. Ventral premotor really increases with number of object-implied actions. So we think it shows that it's important for or reflects a level of competition in action selection, but this is not true for pantomime, okay? Ventral premotor is not modeled, or its activity is not modeled by the number of implied actions in pantomime, because here your selection is not based on the implied actions, right? That's the important difference. Of course, we get a main effect for pantomime because we have an unrestricted search. So we get huge premotor activity for pantomime versus action, of course, because your search is unrestricted, right? But it's not parametrically quantified by the number of implied actions. But what you also see here is that adjacent ventral prefrontal is engaged as well, and this is what we address here. So is the ventral prefrontal perhaps engaged because there's an attempt to integrate consecutive actions, okay, or conflicting information? And what we did here is we assessed the parameter goal relatedness between two consecutive actions, again in a different sample of subjects, and asked them just how much are they related with regard to a common goal. Very strongly, then, or very often, then they had a high goal relatedness, or very rarely, then we assign a low goal relatedness value. And what is also an additional factor here is what we manipulated was whether there was a new object in the second action or not. If there's at least one common object or not, because the idea was that if you re-encounter the same object, it should be a big incentive, so a great incentive to integrate both, right? You just see the object and come back to the next, to the last action. So we manipulated these two factors independently. So high goal relatedness with and without a common object, and the same for low. So these were parameters. Okay, so what we find now is that ventral prefrontal and only this area increases with weak goal relations. So the more difficult it gets to integrate them, the more activity you have, but only when actions share at least one common object. You need the object as a trigger to integrate. And if the integration is difficult because you have a low goal relatedness, you get an increased activity. So, okay. So integration is hampered by weak goal relation, but triggered by a common object. And so it's, of course, well, the next idea was, are there further kinds of triggers there? So one obvious trigger is the actor, right? If you re-encounter an actor shortly after having seen him doing something different, you should try, or the brain could try, to integrate both, right? So what we did here now, or what we did to test, is the spontaneous attempt to integrate the actions of one actor. Again, there was no integration task. It's just we look at the brain during the unfolding of episodes that were presented in an intermingled fashion. I show you here. So the video sequence is a mixture of different conditions where we have episodes that are coherent with regard to both goal and actor, only the actor, only the goal, none of both. So they are not coherent. And we have question trials. And I show you quickly, just to perhaps make this easier to understand, what this stimulus looked like is, so I guide you through this. You see first, so there's a time Tom making a sandwich, first video. Then again, Tom with a sandwich. You see Bettina the first time salting tomatoes, and you asked whether this was salting tomatoes. Thomas back with his sandwich. You see the first person making coffee, you see him never again. Bettina's back, now switching the goal. Thomas back with a sandwich. Then Bettina. Again, a different action, no goal coherence. The coffee making group, next step. Question. And so on and so on. Just perhaps we wait for the blue conditions. So Bettina again, Bettina switching. And then you get one actor with one action, and again, you don't see him again. Okay, doing something. Okay, it's all coherent. And your task is just sometimes to say what you saw in the video before, right? So what we see here, what we are interested in, is the increase in brain activation from one trial to the next within an episode. That is either coherent with regard to goal and actor, only goal, or only actor. What we see is that if you see the actor again, if you re-encounter the actor, you have an increase from video to video in certain areas, especially in the prefrontal cortex. I'm focusing more on an area that only emerges if the actor is not acting goal coherent. And this is inferior or ventral prefrontal cortex, so our hypothesized site in the brain. Okay? And the very same area decreases from one video to the next if the goal of a group is coherent, even if the actor switches all the time. Right? So this is, I think, strong evidence for the idea that ventral prefrontal is relevant or is spontaneously engaged in the integration of these consecutive actions and with regard to the goal, right? So the next, just quickly, rooms, of course, are also associated with certain actions. So there might be a bias to integrate actions with the room. So the idea was here whether there's an activity increase in ventral prefrontal, the very same area, in incompatible rooms, although they are not task relevant, right? So we had neutral, compatible, and incompatible rooms with certain actions. They're just, again, the same task as before. You see we have an increase, again, in ventral prefrontal cortex for actions in incompatible rooms. And we replicated this also in pixelated videos showing that there's a room manipulation conflict, not a room object conflict. That's very important, of course. So pantomime is equally, shows the same effect. And importantly, this conflict costs time. So we are slower in recognizing actions in the not compatible room. And so the idea is, again, it could be a kind of overarching goal that is searched for that resolves the semantic conflict. Some weeks ago, my 4-year-old son and I had a little conversation about this picture. That's a picture of a museum in Bielefeld. And he asked me, are there cows or horses in there? And I said, no, I think this is rather a museum. And he asked, there's stuffed cows in there. Okay, and that just to remind you that, of course, associations between rooms and actions have to be learned. Okay, they are not they're born, not inborn. So what we were interested here was whether we can tackle the onset of incompatibility effect in children. When do they start to care for rooms? There was a huge study in Cologne, and they only were just were showing them pantomimes and were just looking for recognition rates. Okay. And these are the data. What you see here is that, in a way, unfortunately, in each group, starting with the already 4-year-old, they really care for the room, but they benefit from a compatible room. So they are better in recognizing a kitchen pantomime or cooking pantomime in a kitchen than in a, let's say, I don't know, other room. Okay. So we have to go for even younger children. So I've showed some evidence for the fact that or the brain at least, exploits objects, room, and actors, implying manipulations, actions. And obviously, there seems an urge to integrate them, so it comes with costs. There's an investment, okay, in making the situation coherent. And unfortunately, the situation is much more complicated because, of course, we have a triadic relationship here, okay? Manipulations, objects, and rooms show a dependence on each other. And what you can show is that you can make them more or less coherent. You can manipulate the relationship between them just by making them more or less coherent by showing pantomimes, okay? So, and what you see here now is that the brain cares for the coherence of this triadic relationship. You can show that if you can enhance the manipulation conflict, you get a certain higher activation, or you can increase the object conflict, and you get fusiformis again. So the brain cares for integration of all information, even if in the subject down. So to summarize my talk, I hope I could show some evidence for the processes that are going on in the brain when we are facing manipulations, actions. So we exploit object, actor, and room information. And even more, we care for recent encounters of this types of or information. And of course, we exploit our long-term knowledge on frequencies, for instance, certain persons, rooms, and environments, and so on. And just to end with a little speculation that I'm in the moment pretty interested in is, obviously, there's a spontaneous use and integration. So the question is, why does the brain invest so much energy in integrating? It does not have to. It's not very. It seems to be not so efficient for the moment because it cares for information that are not required for the task, right? So the idea is that maybe it's not always about optimizing the current prediction, but train for future predictions. Okay, so enrich your model. And so this also dovetails with a certain problem that is currently discussed in the predictive coding account, the darkroom problem, saying that if the easiest way to cope with prediction errors is go in a dark room and stay there, right? You are a perfect predictor, but this is not biological. So I think these findings somehow imply that we not only exploit, but also explore information out there. And this active search for information will lead to the situation that there, of course, is more surprise in the moment, in the short run, but less in the long, and it seems that the brain likes that. Okay, oh, sorry. So thanks for your attention, and thanks for the coworkers. Sorry.